So first, I would like to thank Brian, Jim for organizing this wonderful event. So and having me here, so that I have a chance to meet the real person behind GSAS. Otherwise, I would think it's AI. So, anyways,
maybe both.
So my name is Hui Wu. I'm the instrument scientist of BP1 powder diffractometer at NCNR. I'm also a materials chemist. So we are doing materials development for various energy applications. So once we discover or develop new material, we want to diffraction, determine the structure, and then we do refinement. So I have been using GSAS for many years. Of course, cannot compare to this audience in room. But anyway, so I just want to take this opportunity to express my appreciation to Bob for creating this marvelous program. Actually, I started to learn GSAS not very long ago. In 2003, I was still a PhD student with Professor Peter Davis at the University of Pennsylvania. And we were working on some ceramics with perovskite structure and focusing on cation ordering and its impact on the dielectric properties of those materials. So in particular, I was working on this barium lithium niobate and barium lithium tungstate binary system. Both end members are hexagonal perovskite with phase-shared octahedra. And then I discovered the existing of some cubic perovskite in some solid solution range within this binary system. And then, which means this ABO3, in the ABO3 single perovskite structure, the one type B cation will split into two different sites, and then they alternate in different orders. So, because I have three elements in this system, three elements for B side at this system, so I want to understand how they distribute on two sides, and also want to determine the location of lithium and oxygen, particular for lithium, I also want to determine its occupancy. And for oxygen, I want to see if there's any octahedral distortion upon cation ordering. So my advisor, Peter, suggested me to do diffraction, neutron diffraction at NIST. And then he and Igor Levin from materials division got some beam time. And because I was going to do neutron diffraction, I have to learn how to analyze my data and do refinement. Then Paul, he was a senior graduate in our group at that time. So he gave me his GSAS manual. So I don't need to print out the 224 pages. So that's the first time I saw Bob's name. So anyway, and later with help from Igor and Brian was in charge of BP1 at that time. So I successfully did my first neutron diffraction experiment. I got the data, good data with expected peaks from superlattice, and then without breaking the instrument. And then I came back and then started to learn GSAS. Fortunately, Brian developed this expert GUI interface for GSAS, which is very friendly, especially makes the learning process much easier and quicker for beginners like me. And then I managed to teach myself, learn GSAS, and finally did the refinement. And then based on neutron diffraction data, we finally confirmed our hypothesized model. It should be niobium distributed on both sides that will maximize the charge and size difference between those two B-side cations and promote cation ordering. And we also determine the position of oxygen too, and we indeed observe some BO6 octahedral distortion, which will elongate the B2O2 bond length, so that will alleviate the overbonded oxygen too. That's oxygen between the two smaller and more highly charged B-side cation. And then later that year, 20 years ago, I came to NIST and do another experiment, neutron diffraction experiment on the calcium and the strontium analogous compound. And then we published the results. These are my first two scientific publications in English. So, After a good experience with neutron diffraction at NIST and refinement with GSAS, and 2 years later, after I graduated, I came to NIST and started my postdoc research. So my first project is about hydrogen storage. And then over the years, we've done a lot of work on various hydrogen storage materials, from porous crystalline frameworks to various hydride. But fortunately, I started with some very simple interstitial metal hydride. So in retrospect, I see these materials are simple for two reasons. First, their crystal structures are indeed simple. So if they have large cell, then they will have high symmetry. So those atoms will be at the special site. If they have small cell, for example, strontium and nickel hydride, it's a triclinic structure, but the unit cell is very small. So I have only a few number of parameters to refine. And then for reason two, because I was working at CNR, I have easy convenient access to powder refractometer. I have to thank Craig for always supporting me and giving me beam time whenever asked for. So simple structure plus high quality of neutron diffraction data makes the structure determination and refinement very straightforward. Then I have time to refine my refinement skills and then to get further familiar with and understand the process of structure determination and refinement. And then also I have time to think about those materials that I was working with. For example, those interstitial metal hydride, the interaction between the hydrogen atom and the metals are relatively weak. So the materials can release and absorb hydrogen at relatively low temperature. However, the hydrogen content of these materials are still not sufficient for practical hydrogen storage applications. So I want to work on some system with higher hydrogen capacities and lower dehydrogenation temperatures. So I move on to other more complicated systems. For example, some complex hydride. Here I'm just showing an example of ammonia borane. This is just a molecular structure of ammonia borane. It contains nearly 28% of hydrogen, but its dehydrogenation property is very problematic. So it decomposes with very sluggish kinetics, and the decomposition is also accompanied with some side reactions with release of unwanted gases. So then we developed these metal amidoborane compounds by reacting metal hydride with ammonia borane. So these compounds shows greatly improved dehydrogenation properties compared to ammonium borane in terms of accelerated kinetics, reduced dehydrogenation temperature, and suppress or minimize the impurity gases. And interestingly, they all have very fascinating crystal structures. So we were able to determine structure based on polar X-ray diffraction data. And of course, because these are lightweight hydride materials, so we also did EFT calculations to relax the structure and get an optimized orientation of those amidoborane ion with lowest energy. And then once we have a proper structure model, we want to refine the structure. But ideally, we should do neutron diffraction. But as you can see, those compounds contain boron and hydrogen, so we have to do isotope labeling. And also, we need a large quantity of sample for neutron diffraction, which is very time-consuming and costly. So then we have to rely on X-ray diffraction powder data, and then we have to constrain those amidoborane ions with rigid body. And then back then in the old version, when we construct rigid body, we have to manually draw those figures on lab book. So we have to define the coordinates and the translation vector of the atoms within a rigid body. Here I'm just showing you a couple of examples I was working with back in 2006. I think that just picture took from my lab book number 2. So crystallographers like ordering, so yeah. So then after we define the rigid body, we have to input them into GSAS with origin and a rotational angle of rigid body in crystallographer axis. And then with help of rigid body provided by GSAS, then we can refine the structure of those compounds by using X-ray diffraction data. And then we also developed other similar lightweight hydride materials within this ternary system. And still, sometimes I'm not still feel very comfortable about determining lightweight hydride using X-ray diffraction data. And sometimes I collect the neutron vibration spectrum and calculate phonon density state and just compare them, see how they agree each other. And just show example of neutron vibration data collected on sodium, magnesium, and amidoborane. You can see the observed spectrum and calculate spectrum. Actually, they show a fairly good agreement, and especially those neutron vibration spectrum can pick up some signal phonon modes, which corresponding to some signature structure characteristics. For example, in this system, we determine from the determined structure, we found magnesium will only interact with nitrogen end of the amidoborane. And indeed, we observed the stretching and bending modes between the magnesium and nitrogen. So, this just provides some indirect evidence for the structure we determined. And then with further development of my research, we found some compounds actually can also exhibit excellent superionic conductivities. So, for example, this closal and needle polyborate or polycarborate. So, these compounds in general, they will exhibit order, phase order, disorder, phase transition. So, at high temperature, those cage-like ions, they will disorderly orientated and behave like a spherical object. And then those sphericals will arrange themselves in a FCC or BCC type close packing arrangement. And then that will create a large space for small cations to move around. So in the disordered states, we will see ionic conduction. Well, below phase transition temperature, those polyhedral anions will have a definite orientation. So we call it ordered structure. But for all those compounds, for the high temperature disordered phase, they will have a more or less similar structure, just depending on different packing pattern, BCC or FCC or even HCP. But for low temperature, they will have a different order structure because of the different size and shape and the polarizability of those cations. So we want to know the structure of those compounds at low temperature. Unfortunately, we always have powder samples, cannot do single crystal, and also, as you can see, the boron-rich materials. So again, we have to rely on X-ray powder diffraction data. You can see how complicated they are. It's a pain to construct the rigid body just on paper. Well, fortunately, GSAS evolved with our research development. Now it can automatically generate rigid bodies just by selecting atoms from the atomic list in XP file. So with that function, that will enable us to refine many more complicated structure. Here, just an example. For example, the potassium CB9H10 compound. It forms a disordered structure, just like the example I just showed you, sodium B10H10. It forms a FCC type close packing. And then at the room temperature, it forms ordered structure with definite orientation of the CB9H10 ions. And upon further cooling, it will convert to two low temperature phases. And those phases are always stay together and even down to the base temperature. I don't want to go to details about how the phase convert to each other. I just want to mention, for example, for the low temperature phase 1, it has 4 independent CB9H10 ions at general site. And we know each anion will have 20 atoms. then we will have 80 independent atomic positions, atoms. And then we also have 4 independent potassium. So the number of the total number of the parameters need to be refined will be enormous. So again, with help of rigid body constraint provided by GSAS, we were able to refine those structures just based on X-ray diffraction data. Another example is magnesium boron hydride adduct with ethylene diamine. This compound contains a lot of hydrogen, so it can be used for hydrogen storage. And also, more recently, other researchers found that this compound can also exhibit conductivity at high temperature. So again, we only have live X-ray polar diffraction data, and as you can see, for example, the triethylene diamide will form a rhombic structure, which is a large unit cell. For the tetraethylene diamine, it forms a triclinic structure. So to refine the structure, we see the structure. Magnesium will coordinate with 3 acetylene diamine and form this magnesium triethylene diamine complex cation. So again, if you want to refine it, we have to put rigid body constraints on ligand. With help from GSAS, we were able to refine the structure. And here just a few more examples of various materials that we developed, and we determine structure and refine the structure using GSAS. So besides the hydride materials, we were also working on some porous crystalline framework materials for various gas absorption related applications. So we're interested in the structure of the framework materials themselves. For example, we can refine the structure with proper rigid body constraints on those ligands, organ linkers. But we are also interested in determining the absorption site of small molecules within those frameworks. So usually to do that, for rigid frameworks, the process is very straightforward. So we usually collect a pair of diffraction. Pattern 1 is from the empty framework, and then we charge the framework with the gas we are interested in. And then because for rigid morph, the structure will not change upon gas absorption. So we just compare the scattering difference of the peak intensities. And GSAS provides this wonderful function for Fourier difference analysis. So we just, it will do Fourier difference analysis and export Fourier difference map. And then we can impose the structure on top of the map, and the highlighted scattering difference will indicate the possible absorption site for gas molecules. So with this function, we have been able to determine the absorption site for various gases in frameworks, for various gas absorption applications. For example, hydrogen, methane, carbon dioxide absorption, separation between different hydrocarbons, and water separation, etc. So once we determine the absorption site of those gas molecules within framework, then we can understand the interactions between the molecules and framework, so that we can further modify the framework materials. For example, we can tune the pore size and pore geometry so that the framework can accommodate similar shape and size molecules. We can also tune the chemistry of the framework so that you can include open metal site with coordinated metal, or we can introduce functional groups to enhance their affinity to particular gas molecules. So we now, with the advancement of materials development, now GSAS also evolved to a more powerful GSAS-II. So it now can handle more data set, more complicated structure with faster computing speed. And for the 2 functions that I just mentioned, rigid body and Fourier difference analysis, GSAS-II also updated very significantly. For example, for the rigid body, now we can not only automatically generate the rigid body, we can also move and manipulate those rigid body to the place that we desired. And for the Fourier difference map, previously we have to export the map in grid file and then plot it with crystal structure in other software. Now GSAS-II can handle it itself. So now we can directly visualize the difference, Fourier difference together with structure, and then we see the missing components and then update the model instantly. So of course, there are still many things. I don't have time to talk about the treasure box of GSAS. And I have still many things to learn. I'm still learning. So with that, I would like to thank Bob. The more I do GSAS, the more I feel grateful for the tremendous effort that you have devoted into this phenomenal program. So thank you, Bob, and thank you for listening. So just a happy birthday, son.